Hey everybody. So I want to start us out by thinking about a little experiment, okay? So suppose you have a, let's say a cable technician that has guaranteed they will arrive between 12 and 4 p.m., okay? And for the sake of this problem, let's pretend that we are confident that they actually will arrive in this time, that they always do. And let's also say that it's equally likely that they'll arrive at any time in between here, right? They're not aiming to get there at 12, but they might be a little late. There's an equal opportunity or equal likelihood that they'll arrive at any of these times, okay? And so a question we might ask is, what is the probability they arrive between 1 and 2 p.m. Okay, so you might have some intuition about the answer to this based on what I've already written. I want to solve it in a particular way because we're going to build up some intuition and some techniques for solving some things that maybe don't leap out at us. And if you're not sure how to answer this at all right now, that's fine too. So let's name a random variable. I'm going to call x equals, let's say, the arrival time of our technician. And in particular, I'm just going to count it as hours past noon, right? So just kind of setting noon as our 0. And then, so if they arrived at 1:30, they'd be 1.5 hours past noon, right? Okay, so that's our variable. But I want to notice, and this we haven't done this in any of these videos yet, this is a continuous random variable, right? So everything we've been looking at previously were discrete random variables. They had outcomes that could be counted, right? We only had a particular set of values. The arrival time, right? This is a continuous. The time can come in any intervals, any increments between noon and 4, right? And so we have to deal with continuous data a bit differently than we do with discrete data. So let's draw ourselves a picture of the sample space, okay? Now, there are many ways you might come up with to do this, and I'm going to pick one that's going to be useful in some things we do later, okay? And one thing we should think is when we have sample spaces with discrete variables, when I've been looking at flipping coins numbers of times and things like that, we can write down all the possibilities. I can't write down all the possible times between noon and 4, right? We can chop up seconds as small as we want, so there's going to be an infinite number of times between noon and 4. So what I'm going to do instead is I'm going to represent the arrival time. I'm going to make a little graph. So I'm going to make this axis 0. That's 0 hours afternoon until 4 hours afternoon. Okay. And I want to represent how likely each time is in a relative sense with a line above this graph, right? Well, in this case, everything's equally likely, so I'm just going to show that they're all the same likelihood by drawing a line above the graph, okay? And if they were more likely to show up in the middle, I would have made it taller in the middle. We'll do some examples like that later, but I'm just starting off with kind of the simplest idea. And the way we'll think about probabilities, this box that I've now created, right? This shape between the two endpoints of our data, right? This is all of our data. The arrival time is represented by this horizontal axis, and the height above this is the relative likeliness of likelihood of each time in here, right? And the fact that it's flat means they're all the same, okay? The way we'll represent probability in this graph is with area, and this is going to be a technique we're going to use for all of our continuous variables. So let me make that more clear. Let me put in some divisions here. So I've got, right, our hours past noon, and we were wondering what the probability between one and two, right? And so this area is what we'll use to represent the probability of arriving between these two times, okay? So notice what I've said, that we're representing areas here, and that this line above represents how likely things are. If, for instance, I had said it was more likely for them to arrive between 1 and 2, the line would have been bigger there than the other places, and that would mean the area would be increasing. And so that would match with what I said, right? That the bigger area for the places that were more likely. So we'll dig into that idea a little more later. So let's figure out a few more things, okay? So what we're trying to compute right now is the probability that x is between 1 and 2, right? And I just told you for continuous variables, we're going to use area. Well, we've got an area of, my drawing looks a bit like a square, but that's because things aren't to scale. It's a rectangle, so we're going to say this area is going to be the length, or let's call it the height, times the width. Right? It's easy enough to see the width from this picture. It's between 1 and 2, that's a width of 1. But what is the height? Okay, we're going to have to come back to that question. Let's ask ourselves a little bit of a different question. What is the probability that our technician arrives between 0 and 4 hours past noon? Okay, well, as I said in the setup, we guarantee that they'll be there between these times. In other words, it's a certainty. This might not reflect real life, but let's assume that it's certain for the context of this problem. That means if it's certain to happen between 0 and 4, we know the probability is equal to 1. That's the meaning of a probability of 1, right? But I also know that this is the area under this entire box, right? The height times the width, right? So this 1 has to be equal to the area of this entire box. Well, I already know what the width is. Width is 4, from 0 to 4. So if I divide both sides by 4, I get my height. Right? So the height of this has to be 1/4 because the area under the entire thing has to be 1. Okay? Which means now I can take this information and go back to this problem where I was trying to compute the area of this box, but I didn't know what the height was. I now know that it's 1/4. I multiply that by the width of 1, and I get 0.25. Okay? And that is the probability. If we are very careful, we might see that the units work out very nicely. The width is between 1 and 2 hours, right? Remember, these are hours past noon. The height, this number 1 is a probability. It's just a number. We divided it by a width of 4 hours, so it has hours in the denominator. So we had hours in the denominator, hours in the numerator. This cancels out and gives us just a number, which is what we want our probabilities to be. So this idea, right, that we're connecting area to probability, that is the big takeaway from this. We're going to look at graphs like this in a bit more detail in a later video. I'm using it as an example right now. Don't get too hung up in the details. The biggest piece of information we want to pull away right now is this idea of area and relating it to probabilities. So let's summarize some of those ideas, and then pull in some other things. So what we're looking at right now, or what we just looked at, is what we would call, we had a continuous random variable, right? In that case, we were looking at the random variable x. The data was continuous. And we want to come up with probability distribution functions, right? Remember what those are. They tell us about the probabilities of a random variable in terms of a probability distribution function gives us all the possible probabilities for a random variable, okay? The way we're going to get there with these continuous random variables is first starting with a probability density function, right? Not the probability distribution function, okay? Which is this picture that we just looked at, right? That is this line. For this particular one, it's this line, right? It is a curve. Let's just say it's a curve that shows the relative likelihood of each data value for the random variable, right? In the places where it's higher probability, and in the places where it's lower likelihood, right? It doesn't give us the values of probability, right? The probabilities are determined by area under the density function over the interval of interest, right? So for example, I'll just sketch a little picture, right? Maybe I have some random variable, right? Some experiment, and let's say all of the outcomes are between A and B, okay? And let's say I had a probability density function that looked like this, okay? Right? What this is telling me is that things in this region are the most likely, things over here are less likely, things at the end over here are very unlikely because they're getting very close to zero. And if I wanted to know the probability that my random variable was between two values, I would have to compute the area under the curve, okay? It's always going to be the case that the area under the entire curve is 1. Okay? It's always going to be the case, so let's write that down. The total area under curve equals 1, right? Because if this is our entire sample space, if our variable can be between A and B, then this represents all the possible things that can happen. So the probability has to be 1, it's certain, and the probability is represented by the area, okay? That's one thing. The horizontal axis, this always represents data values, right? Just like when we built our histograms, we put our data values across the horizontal axis with the frequencies along the vertical axis. There is a parallel here, right? When you draw a histogram, the taller the bar is, the more likely, right? The higher the frequency, the more likely that outcome is. We're seeing a very similar thing here. It's not by accident, right? These are kind of analogous to those histograms for our continuous data. Not kind of, they are. They're extremely analogous to that. You might be wondering how we find these areas. Well, for the most part, we either find them like we did here, where there's some very simple geometry that we can use, right? Here we had an area of a rectangle. We might have things like triangles or trapezoids, things that are pretty straightforward. So we find areas, we'll say with geometry. If you take a more advanced course in calculus, you will learn how to, you might learn some calculus, in probability, you might have to learn some calculus to find these kinds of areas. But we're not going to do that in any of these videos. What we will use instead is we can use technology. right? So like when we did the binomial and Poisson distributions, there are some formulas out there that are a little complicated, but we can just use our technology to find them for us. We just have to understand how to formulate the problem. We might also occasionally refer to tables, though if we're working on a computer, there are tons of calculators online that will find these areas for us. Again, that doesn't mean it's easy. We have to find out what areas it is we want, things like that. I've also been sort of hinting at something without saying it precisely. We are always going to be asking for areas, probabilities over intervals, right? So if this was the probability density function for a random variable x, right? These were data values of x. This is our random variable. If it's continuous, we're only going to ask questions like, what's the probability that x is between c and d? Or what's the probability that x is greater than d, right? That would be asking about this area up here. We won't ask questions like, what's the probability that x is equal to a number? This is very different than we do with discrete random variables, right? This is there's kind of a complicated reason why. Let's just say that it's a rule, right? If we're talking about areas, equaling d is just a single line which has an area of 0, so those are always going to be 0. So I guess you can ask it and give the answer of 0. It can get into some pretty heady theoretical discussions about why that's the case. Maybe one answer is this. For instance, in the example I started with when we had our technician coming, how would you measure exact arrival time, right? There's a lot of discrepancy, right? At what point has this person arrived? When they cross the threshold, which part of their body, where do you draw the line where the end of the, there's a million different reasons we could say it's impossible to know exactly what moment they arrive, but we can give some intervals over their arrival time. We don't need to worry too much about that, and we won't worry too much about that in these videos. So with that in mind, it also means things like P of x greater than d is exactly the same thing as the probability that x is greater than or equal to d, right? It's the area of this shaded region. Does it matter if we include this line or not? And it doesn't, okay? It doesn't change the area. Just like if I drew a square and said it's 1 by 1, the area is 1, and I said, all right, but don't include the outline, right? Well, it's still a 1 by 1 square, okay? It's again, it's a little bit of a dicey topic that we're not going to go too far into. Okay, let's do one last example. The majority of our examples are going to be similar to the one that I showed you. And then we'll do that in some more, in another video. I'll do a bunch of examples with this kind of a distribution. And then we're going to spend a long time doing something called the normal distribution. But let's do one more with some geometry to it that we can solve with simple geometrical rules. So let's say we have the following situation. We've got a pipe leaking some kind of liquid, okay? And let's say we've noticed that, you know, you can imagine that situation where you can see a little bit of accumulation of liquid on the end of something, right? And it builds up and gets bigger and bigger. And then at some point, right, maybe it's hanging off the edge in the bottom underneath this pipe. And then at some point it gets heavy enough and falls off as a drop, right? That's what I'm trying to imagine right now. This liquid that's accumulating until it gets heavy enough to break its surface tension, or it's whatever is connecting it. It's I don't know the correct terms from in the study of liquids. But anyways, we all know, we've seen this kind of thing before, right? A dripping sink or something like that. So let's say we're watching this liquid accumulate, and what we notice is that if I take x equals seconds since last drop, right? So one drop just went, and now I'm looking at when's the next drop gonna happen, right? And maybe I noticed they almost never happen right after the first one. Once in a while they do. They usually wait some amount of time, and mostly happens towards 6 seconds, but they never hang on longer than 6 seconds. I might model this probability in the following way. Here's my data across the horizontal axis. And it never falls off immediately, right? Here's 0 seconds past since the last drop fell. It never falls off right then, but it increases in how likely it is as time goes on, right? As time goes on, it's getting heavier and heavier and heavier, and then it hits some point where it has to fall off, right? It'll always fall. And so this is not a perfect model, but it maybe is some kind of approximation to how a situation like this might work. And so this would be my probability density function, okay? And I might want to answer the question, what is the probability? Actually, let's write it up here. What is the probability the next drop falls after more than 4.5 seconds? Okay, so there's our question. So in our picture, here is 3 seconds. 4.5 would be right there. So what we're asked to find here is this area above 4.5 seconds. Okay, let's name a variable. Let's name the variable d. Oh, sorry, I already did. I named it x, so we'll stick with that. So our question can look like this. What is the probability that x is greater than 4.5 seconds, right? And what we've already said is it's going to be the area, the shaded area, which is a trapezoid. So let's figure out the area of that trapezoid. So some information I might need to know is, how tall is this whole shape? Well, what I know is, remember, the area of this entire triangle has to be 1, but the area of a triangle is 1/2 times the base. So the width here is 6 times the height, which means 1 is equal to 3h, or 1/3 is equal to the height. So I know that this height over here is 1/3, right? I know it's not the scale. It doesn't need to be. I'm just using it to represent things, as long as I have the correct numbers in there. Okay? So I want to figure out the area of this trapezoid, right? Well, let's write down the formula for the area of a trapezoid. Trapezoid is 1/2 base 1 plus base 2 times the height, right? The height in this case is this distance. Base 1 and base 2 are the two bases of the trapezoid, right? It's on its side, but we take the average of these two and multiply it by the height. Okay, that's the idea. So I already know the height. That's this distance here. Let's put that in. This distance is 1.5. Let's do 3/2 since I've got some fractions going already and I want to stick with one or the other. Base 1 and base 2 are these two heights. We already know one of them is 1/3. Let's call that base 1. We just need to come up with base 2, this in here, right? So I'm going to figure that out with a little bit of geometry. So you may or may not remember similar triangles, but I'm just going to do a little sketch down here. I've got a triangle that's 4.5 wide, and it's got a height of base 2. That is this triangle here, right? It's with the base here is 4.5. The height here is the one we're looking for. And it is similar to the big triangle, the whole thing, that's 6 by 1/3, right? We know they're similar triangles because they've got the same angle here, and they both have the same, they have the right angle here, which means these two angles are going to be the same. So they're similar triangles, which means their proportions are the same. In other words, let's see, B2 over 4.5 is the same as 1/3 over 6, right? If I take this height over this base, it's the same proportion as this height over this base, which I can solve for B2 as B, oops, let's put it up here, B2 is then equal, just multiplying 4.5 to the other side. I have 1/3 times 1/6. I'm just making this fraction a little cleaner. And then times 4.5. If you work this out, this is going to be 1/4. Okay, so I'll let you compute that as you need to. Okay, so we've got this base, 1/4. I can put it into this formula. I've now got, let's combine these. So I've got 1/2 times 3/2 gives me 3/4. In here, I've got 1/3 plus 1/4, that's 4/12 plus 3/12. So I've got 3/4 times 7/12. Right, I could do a little canceling, and I get 7/16. Okay, and that is the probability that x is greater than 4.5. Okay. Okay. So the biggest takeaway is just the notion of area under these density curves representing the probabilities. Okay, and as far as geometry goes, this is as hard as I would ever, as I'm ever going to explore in terms of figuring them out by geometry. Most of them are going to look like that first example, that are simple rectangles. The ones that are more complicated are typically going to be so complicated that we're going to jump right over this and be using some technology to examine those. But I will dig into that into some later videos. That is it for this one. Thanks, everybody. I will see you next time.